Hello students, I am Dr. Krupa Rasane, Professor and Head ENC, Jain College of Engineering, Belgavi. This is basically the 8th video of Module 4, Power Electronics BE 7 Semester ENC Engineering. We will be referring to the DC to DC converter of Module 4 and we are referring to the textbook of Mohammad H. Rashid, Power Electronic Circuit Devices and Applications. In this particular video, we will be looking into the converter classification. In the previous video, we have seen the switching mode regulator with respect to the buck regulator. In this video, we'll be looking into the boost regulator. So coming to the classification of converters, we have already seen the buck converter, which is nothing but a step-down converter and produces a lower average output voltage than the DC input voltage. In this video, we are looking into the boost converter, that is a boost converter, which will be shown the output voltage is always greater than the input voltage. And next videos will be looking into buck boost converter and choke converters. So these are the four circuits that we had seen earlier, and the buck converter, we have seen the switch coming in series with the voltage power supply, and here in boost converter we can see the switch is coming in parallel with the load as well as the source, and we have this inductor in series with the source. So in for the buck chopper, we have seen the energy only goes to the load when the switch is closes, whereas for the boost, the chopper energy only goes to the load when the switch is open. Okay, so this is what we are going to see. Whereas in choke converter, energy is transferred when the switch opens and when it closes. Now coming to the boost regulator. In a boost regulator, this is the circuit diagram we have seen. So we have the source voltage, we have the inductor in series, the switch is in parallel with the source and the inductor. We have this DM which is connected in series with this load, and the capacitor is connected in parallel with the load. So this is basically the circuit diagram, and this is the switch representation where this switch is replaced by this switch as well as the diode is replaced by a single pole two-throw switch here. So when it connects to 1, it means the switch M1 is on. When it connects to 2, the diode DM is on. And it also signifies two modes of operation. One, when the switch is in this position, and two, when the switch is in this position. So in a boost regulator, the output voltage is greater than the input voltage, hence the name is boost. The boost regulator using a power MOSFET is shown in this particular figure A, and when the transistor M1 acts like a controlled switch and DM is an uncontrolled switch. Okay, why it is called controlled is I'm going to give a gate current here, whereas this simply turns on when it is forward biased. The circuit is often represented by the switches as shown here in the figure B. So the circuit operation can be divided into two modes. One is mode 1, which begins when the transistor M1 is switched on at t equal to 0, and the input current which rises slowly from inductor L and transistor Q1. The mode 2 begins when transistor M1 is switched off at t equal to T1, and the current that was flowing through the transistor would now flow through L, C, load and diode DM. The inductor current falls until transistor M1 is turned on again in the next cycle. The energy that is stored in inductor L is transferred to the load. So this is basically the boost operation, the step-up operation, which is very similar we have done earlier. And the equivalent circuits of the modes of the operation are shown in the figure C, we'll be just showing. And also the waveforms of the voltage and currents, the respective voltage and currents in the figure D. For continuous load current, we have been showing, and the current rises and falls linearly. Assuming that the current increases from I1 to I2. So here we see the switch representation of the boost regulator. And we have the mode 1 and mode 2 operation, and we have the waveforms on this right hand side. So in mode 1, the switch is going to be closed in this here, and here what happens is the S2, the load gets disconnected from the input supply. So we have one basically a closed loop here, that is Vs, L and back here, and another closed loop is between the load and the capacitor, that is current flowing here. So what happens here, if you see in mode 1, the load is disconnected from the supply. So in this diagram, we are looking at the output voltage VA that is coming across the load. It's a resistive load, and we see that from 0 to T on, or from 0 to KT, the output voltage is 0 because it gets disconnected from the input. During this time, if you look at the inductor current rises from I1 to I2. We are considering the inductor current to be a continuous load current. Okay, and it goes from I1 to I2, or like sort of charging this inductor, this. But if you see that we are assuming that the load current is going to be constant DC. This is the output current. Okay, and if this is the case, during the on time when the inductor is charging here, the current IA is still flowing, right? And that is flowing through the capacitor in this direction, and hence it will be the reverse current that is flowing through the capacitor. So if you see at the capacitor waveform, this IA will be represented as the negative IA because the current flowing through the load is IA but in the reverse direction. Okay, so this is basically your mode 1 that is happening. And in mode 2, when the switch goes in this direction, that means this particular loop opens up and the diode is going to conduct here. S1 conducts and the load gets connected to the input supply. That means the load is now going to have this voltage at the output, okay, from T on to T off. So this is basically the off time of the circuit in mode 2. And during that time, the inductor current will, the voltage, basically if you see, the voltage is going to rise from a low value to almost beyond Vs, because this additional voltage beyond Vs is getting from the inductor value stored. So the voltage stored in inductor and the source comes in series, and the load voltage will be higher than Vs. That's why we say it's a step up chopper. Okay, and during that time the input voltage is also connected to the load, so we show that the voltage is equal to this kind of voltage. Okay, and then what happens to the inductor current? Inductor current is going to discharge through the load. Now it is no longer charging, but it is getting sort of discharging its energy. So the current falls from I2 to I1 in this case. Okay, and if you look at the capacitor now is going to, the current is going in this direction. That time this current I1 is going to split between IC and I0. So the current which was earlier going like this, it now reverses, becomes positive, and it shares this I1 value, right, which is equal to the IC plus I0. Now I0 we are assuming to be fixed DC. So the other part other than I0 will be taken over by, or the ripple will be taken over by the IC. So IC will be almost like this, and it will be equivalent to this, but it will be shifted with the negative here during the switch on time, and this is the off time. Okay, and here we are seeing the capacitor voltage. When the load is discharging through this capacitor, that time the voltage is slightly dropping. And when the in mode 2, when this current is charging the capacitor charges. So there is a ripple voltage that is going to come across this particular capacitor. Okay, so all the ripple current will be going through this, and hence the average value, which is equal to the output load voltage, will be coming across this. So delta Vc is the ripple voltage across the capacitor, and delta I is basically the ripple current that is flowing through the inductor. So assuming that the inductor current rises linearly from I1 to I2 in time t1, right? So we are seeing this. Now let us look at the equation. So what you will see is Vs will be nothing but equal to L into di by dt. So L is nothing but the inductor. Di by dt is nothing but the rate of change of voltage current, that is I2 minus I1 upon the time interval that is during the on time, that is T1. So this is equal to L into delta I by T1, right? Or I can write T1 is equal to delta I into L upon, I bring this Vs below. And the inductor current is going to fall from I2 to I1 in time T2. So the next, this is T1 and this is T2. So during T2, the current is going to fall from I2 to I1. Then, and at time, the input supply is connected, that is mode 2 is there. So the voltage across the inductor will be Vs minus Va, and that will be equal to minus of L into delta I by T2, because this time the voltage across the inductor is going to reverse. So you will have minus L into delta I by the time duration, that is T2 here. So with this, I will get the T2 value as delta IL upon VA minus VS. The negative sign will interchange this VS and VA. Where delta I is equal to I2 minus I1 is the peak ripple current of the inductor L, and hence delta I can be delta I becomes equal to, here also I've got delta I, here also I've got delta I. So delta I becomes equal to Vs into T1 upon L. Vs into T1 upon L is equal to, in this particular, Va minus Vs into T2 upon L. So I equate both these delta I from both these two equations, and I will be getting the and also I'm substituting T1 as K into T and T2 as 1 minus K into T, and this will give me the average output voltage, and that average output voltage will be equal to VA is equal to Vs into T by T2, that is nothing but equal to Vs into 1 minus K. K is the duty cycle, which is equal to T on upon T off. So substituting, I'll be actually deriving the step up chopper equation only, which is equal to Vs upon 1 minus K. So boost regulator is nothing but the step up chopper. So I got this equation for VA, which is equal to Vs upon 1 minus K. And with this, if I take 1 minus K on the left hand side, I'll get it equal to Vs upon VA. And substituting K as equal to T1 by T, that is equal to T1 into F, I will get again T1 is equal to VA minus Vs upon VA into F. So this is the equation for T1. Now assuming a lossless circuit, that means whatever input power I'm giving, the same output gets delivered at the output. So there are no loss in between the circuit. So I can say easily that the power at the input, that is Vs into Is, is equal to power at the output, that is Va into Ia. So substituting this is equal to Vs. Va is nothing but Vs upon 1 minus K into Ia. Okay, I will be getting Is, that is the input load current, is equal to the output load current upon 1 minus K. Now let us look to the peak-to-peak inductor ripple current. So that is, your T1 is equal to delta I L upon Vs, and T2 is equal to delta I L upon Va minus Vs. So to calculate the peak-to-peak ripple current, the switching period T can be found from T equal to 1 by F, which is equal to T1 plus T2. So I will substitute T1 as delta I by delta L I into L upon Vs plus delta I into L upon Va minus Vs. So solving this, I will get a simple expression delta I L into Va upon Vs into Va minus Vs. And this gives me the peak ripple current equation. Delta I is equal to Vs into Va minus Vs upon F into L, means T is F, right? 1 upon F. So F into L into Va. So this is the expression, or I can simply write delta I is equal to Va minus Vs, okay, upon Va. That is going to give you the value of K, okay, and Va cancel. So we get Vs into K upon F into L. So it's simplified version, but you can remember this equation better, and you can substitute the values and get it directly. Next is we have found the ripple current. Now we have to find the ripple voltage. So peak to peak capacitor ripple voltage. Ripple current we get it across the inductor, and the ripple voltage we get it across the capacitor. So when the transistor is on, the capacitor supplies the load current, right, from T to T1. And the average capacitor current during time T1 is IC equal to IA. I told you the IA is, we are assuming it to be fixed or constant. So the capacitor has to carry that current during the during this particular period. And the peak to peak ripple voltage of the capacitor delta VC is equal to the VC value minus VC at T equal to 0. So we know that VC equation is equal to 1 upon C integration from 0 to T1. That is the time the capacitor is discharging to the load. And that becomes equal to 1 upon C 0 to T1. Current is going to be IA into dt. So simplifying this, I will get IA into T1 upon C. Now substitute T1. We know T1 is equal to Va minus Vs upon VAF. We just got it in the previous slide. So I substitute the value for T1 and I get the ripple voltage delta Vc, which is equal to Ia into, right, Ia into Va minus Vs upon VAF into C. So if I substitute Vs upon Va as 1 minus K, and then I can get a simplified expression, that is delta Vc equal to Ia into K upon F into C. But we need not remember this. We can remember this particular equation for any problem solution. Okay, now what is the condition for continuous inductor current and capacitor voltage? Now we have done the what should be the critical value of the inductor and the critical value of the capacitor, so that the current through the load is going to be continuous and it is going to be I. Okay, DCI. So how do we evaluate that? Now we know that delta IL is equal to 2 into IL. This I have also explained during the buck regulator. Since the ripple current goes from I2 to I1, the average of the current is nothing but the DC current. So the inductor current is equal to delta I by 2, or delta I is equal to 2 twice IL. Now delta I we already know is also equal to Vs K upon Fl. So I will write it K into Vs upon Fl, okay, for delta I, and this is equal to twice the inductor current IL. In this case, the inductor current is same as the supply current. So 2 into Is. We know that Is is Ia upon 1 minus K, and we also know that Va is Vs upon 1 minus K, and hence I get this expression. This is equal to 2 into Vs upon 1 minus K the whole square. Try to substitute and get this particular answer. Now simplifying this, taking the L on the left hand side, that gives me the critical value of the inductor, which is equal to K. This Vs cancels, K into 1 minus K into R, because Ia is nothing but Va by R, R upon 2F. Okay, so this is going to give me your critical value for the inductor. Similarly, we have to look at the critical value of the capacitor. So if Vc is the average capacitor voltage and the critical condition for continuous conduction, then the ripple voltage delta Vc is nothing but 2 times Va. Okay, so we know that delta Vc we have already evaluated. It is Iak upon Fc. Substituting for delta Vc as Iak upon Cf, that becomes equal to 2 times Va, and we know Va is nothing but the product of Ia into R. So which gives a critical value of the capacitor Cc as Cc is equal to C in, which is equal to K upon 2Fr. So we have evaluated the critical value of the capacitor. So looking at the formulas of the buck regulator, we know the output voltage is equal to the input voltage divided by 1 minus the duty cycle K. We also know that the supply current is equal to the load current upon 1 minus the duty cycle. This is the ripple current, which is equal to Vs into Va minus Vs upon Fl into Va. Similarly, we have the ripple voltage, which is equal to Ia into Va minus Vs upon Va F into C. And we have the critical inductance value, which is equal to K into 1 minus K into R upon 2F. And we have the critical capacitance value C equal to K upon 2FR. Now, we're looking at the example problem. So the boost regulator in this particular figure is basically having an input voltage. So this is the boost circuit. It has an input voltage of 5 volts. The average output voltage is equal to 15 volts and the average load current that is flowing is 0.5 amperes. The switching frequency is 25 kilohertz. The L value is given as 150 Henry and the capacitor value is given as 220 farads. You are supposed to determine the duty cycle K. We know the input voltage, we know the output voltage, we know the formula, and hence we can evaluate the value of K. The ripple current of the inductor is delta I. I have given you the formula. I can use it directly. And then the peak current of the inductor I2. So peak current is the I2 value. So inductor current, you have to use your judgment here and you analysis and get the value for I2. I have not given an expression for I2 as of now. The ripple voltage of the filter, delta Vc, you have to get it. That formula is available and the critical values of L and C. Okay, so we have to find the critical value of inductor and the critical value of capacitor to get the continuous load current. Now let us move to the solution. What are the given parameters? Vs is equal to 5 volts. The load voltage is 15, frequency is 25 kilohertz, L is given as 150 microhenry and C is 220 microfarads. So from the expression Va is equal to Vs upon 1 minus K, I substitute Va as 15, Vs as 5, 1 minus K. We have to find K. I get 2 by 3, which comes to about 66.67%. Next, I use the delta I formula, which is Vs into Va minus Vs upon FLVA. We know most all the values, right? Vs is 5, Va is 15, right? And F is 25 kilohertz. And L is nothing but 150 micro. So put this 10 to the power of minus 6 into your Va, which is nothing but the output voltage 15. So calculating, I should be getting around 0.89 amperes. Next, let us find the source current. The source current Is is nothing but I upon 1 minus K, and that gives me the value as 1.5 amperes, right? And Ia value has been given to us as 0.5. And the peak inductor current. So we have to find the peak inductor current. The formula goes like this. I2 is nothing but the source inductor plus the rate of change of current upon 2. Very simple expression, right? And if you look at the waveform of this inductor, you will know it has to be Is plus delta I by 2. So that becomes equal to IS we have evaluated as 1.5, delta I we have evaluated as 0.89, and divide by 2 I should be getting the peak value of 1.945. Now we have to find the critical value. Now R is equal to VA by IA, right? So I get R value as 30 ohms. And also L equation we know is equal to K into 1 minus K into R upon 2F. So I substitute the value for LC, right? And I know the values, all the values, and I'll be getting it as 133 microhenry. And again, we know the critical value of the capacitor formula, which is equal to K upon 2FR. And hence, substituting that value, I'll be getting this as 0.44 microfarads. So there are two formulas were there. One is the critical frequency, and for the critical capacitor I have given, this is the simplified version in terms of K that we have used in the formula. So that will become a faster way of solving the problem. Or you can use the bigger formula as well here. So we have been looking in this particular video into the switching mode regulator with respect to the buck regulator. We have seen the circuit diagram, we have seen the modes of operation, we have done the derivation for the output voltage, the ripple current, the ripple voltage, and also we have evaluated the critical value of the inductor as well as the critical value of the capacitor to get the continuous load current. So with this, we come to the end of this particular video 8, and I thank you so much for the patient listening. If you have any doubts and queries, do get back to me. Thank you again.